Hey everyone, in this video I'm going to go over some of the math of solving a couple of different very closely related nuclear chemistry calculations. The key thing about nuclear chemistry is that every single nuclear process is always first order. So the rate law, the integrated form of the rate law, is always natural log of the concentration or amount equals negative kT plus ln of A naught, or the original amount. There's a trick sometimes that we can pull with the A naught that'll make it disappear. I'll show you that in just a moment. The other thing is that that you'll frequently need to use the equation that the half-life, the T1 half, is equal to 0.693 divided by the K value. That's going to come up a lot as well. All right, so we're going to use those two equations repeatedly in these, and some of this is just reminding yourself how to do natural log calculations. So as an example here, all right, we've got consider a nuclear reaction for which 15 grams of a sample decays for 10 years, after which 14.2 grams remains. Calculate A, the rate constant, B, the half-life, and C, how much will remain after 50 years. That should say after 50 years. All right, so we're given an amount, an initial amount, a final amount, and we're given a time. So what we're going to do here is we're going to take that first order integrated rate law and we're going to plug everything in and use that to solve for K. All right. So here we're going to plug in ln of 14.2 grams equals negative. Again, we're solving for K. The time it takes for this to happen is 10 years, plus ln of 15 grams is the original. You can do some sleight of hand here with the logarithms, and if you prefer to do that way and you know how to do it, go for it. I think it's generally easier to just punch this through, so we're just going to do ln of 14.2 over here on the left-hand side and simplify this. This becomes 2.653 equals negative K times 10 years plus ln of 15. We punch that through the calculator. That comes out to be, oops, not ln of 15. Let's just simplify it. 2.708. All right. So now we're going to subtract 2.708 from both sides. That's going to leave us negative K times 10 years. Pardon me. Let's see here. Punching this through the calculator. Oops. I apparently don't know how to do subtraction on my own calculator, so let's try that again. 2.653 minus 2.708. Negative 0.55. Probably could have done that in my head faster. If we divide both sides by negative 10 years, that gives us that K is equal to 0.0055 years to the minus 1. All right? So that's our K value. So that's the first part of what we were trying to do. So this is part A. Part B, I'm just going to squeeze in right here. We're going to do the T1 half calculation. So the T1 half is going to be equal to 0.693 over K. 0.693, by the way, is just natural log of 2. That's where that number comes from in case you're interested. I suspect you're not. That's okay. 0.693 divided by the K value, 0.0055. That's going to come out to be 12.6 years. All right. So notice that the K value, which I left the unit off of, was years to the minus 1/2. When you have 0.693 over years to the minus 1/2, the years goes back to the numerator, becomes years to the positive 1, which is a time unit. So that all makes sense. All right. Okay. So now The last thing we're asked for is how much will remain after 50 years. So this just requires us to plug back everything back in to the calculation. All right. So we're going to do, oops. We're going to do for part C here, we're going to do ln of A equals negative kt plus ln of A naught. So we're asked how much is going to remain, so we need to find the A here. We know the value of k, that's 0.055 years to the minus 1 times 50 years plus, and what, let's see, how are we asked this? How much will remain after 50 years? So originally we had 15 grams, right? All right. So we've got ln of A equals 0.055 times 50. That's going to be negative 2.75. Notice these cancel. Plus ln of 15. Don't know why I keep writing ln. ln of 15 is 2.708. So we're going to do that plus negative 2.75, which comes out to be negative 0.0419. Now, here's, I suspect, the part of logarithm math that a lot of you have forgotten. So you're trying to isolate on A here, right? So we're trying to isolate A. To isolate a variable, you do the opposite of what's being done to it. Well, what's being done to it is it's having the natural log taken. The inverse operation of natural log is raising something to the power of e, the natural logarithm base number. And generally on your calculator, it's going to be right above. It's going to be like second natural log. So it's the function above the natural log. Other calculators have it in other weird places. Just look around. You're looking for the lowercase e, not the uppercase e. Remember, the uppercase e is raising something to the power of 10. This is the natural log base e. Anyway, when you plug this through the calculator, you get 0.9. 0.9, let's call it 6 grams. All right. All right. So the key thing here is just this weird point when you get to here where you have ln of a number equals some other number, and all you're doing here is raising this to the power of e. So e to the negative 0.0419 gives you this number here, and then e to the ln of a is just a. All right? Okay. So here's another question, another example. And what I would suggest is that you pause the video and try to work this yourself. But I'm going to work it through, but it would be really helpful if you just paused it and tried to do it yourself first. Okay? All right, the half-life of a certain isotope is 100 years. Calculate the rate constant K and determine what fraction of the sample will exist after it decays for 500 years. So earlier I gave the half-life equation like this. Notice that K and T1/2 can just switch places, and that's equal to this. This is this old math trick we used a lot in gas law math, where if you have something that's in the denominator in one place, you can just move it to the numerator on the other side, all right? If you prefer, what you're really doing is multiplying both sides by k, and you're dividing both sides by t1/2, which ends up doing the same thing, all right? Okay, so anyway, our k value here is going to be 0.693 divided by 100 years. So 0.693 divided by 100 is going to be, just move the decimal place twice, 0.00693 inverse years. All right, so that's our k value. And then we're asked to determine the fraction of the sample that will exist after it decays for 500 years. So you're going to break out the first order integrated rate law. And actually, there's two ways to solve this, but I'll show you the second one here in a moment. So we're going to do this the mathy way first. So we need to know how much of it remains. So anytime you're asked for the fraction of what remains, what you can do here is make your A naught equal to 1. And what that means is that 1 is like 100% or all of the sample. And then whatever's left is the decimal fraction of what would be, of what the whole would be, or sorry, what portion of 1 is left over, okay? It doesn't matter what the units are here. Logarithms make units disappear anyway. If you like to think of it just in straight up percentages, you could make your A naught here 100, and that would be fine. It's just a little extra work because the ln of 1 is 0, so this just makes everything go a lot faster if you do it this way. Times how many years? 500 years. 500 years plus the ln of 1, again, when you plug that in your calculator, that's 0, so it's really easy. So this comes out to be ln of A equals 0.00693 times 500, 3.465. Don't lose track of this minus sign, by the way. It's really important. Otherwise, you get a really goofy number. Okay, so inverse natural log is raising something to the e power. Negative 3.465. And that comes out to be 0.031. So again, this is if you started with like 1 gram or 1 kilogram, you'd have 0.031 grams or 0.031 kilograms. You could also express this as a percent by multiplying this by 100 and saying 3.1% is going to remain. It's just depends on how the question's phrased and how you choose to answer it, okay? But the way I phrased it was in terms of the fraction, so that 0.031 is the fraction, okay? So that's the mathy way to do it. Now we're going to do this the sneaky other way, which is we could also recognize that the half-life is 100 years, and we're doing this over 500 years. So it's 5 half-lives, right? So after 1 half-life, or 100 years, you're down to 0.5 of what you had to begin with. After 200 years, you have half of that, 0.25. After 300 years, you have half of that, which is 0.125. After another half-life, you're down to 0.0625. And so after 5 half-lives, you're down to 0.31-ish, okay? Which is the same answer we got by doing it the mathy way down here, all right? So you can do this either way. Again, if you want to recognize that this is 5 half-lives and do it the way I showed you over here, that's totally fine. Just make it clear that that's what you're doing so that you're showing work, or you can do it the mathy way and do it like I did down here. Either way is fine, all right? Okay, I hope this clarifies a little bit of nuclear chemistry calculations and kind of dredges up some of your memories of how to do natural logs, all right? Questions, drop those in the comments. Thanks, everyone.